Welcome back to the next video, everybody. So we just finished talking about some of the basic Archimedean representation theory for GL2 over the past couple of videos. In this video, we'll look at some of the p-adic representation theory of GL2. And so first, let's talk about how admissibility and continuity should be defined. The setup is we'll take F to be a p-adic field with ring of integers O sub F, and we'll set G now equal to GL2 of F instead of GL2 of R like we were looking at previously. An admissible representation of G on a vector space V is a homomorphism pi from G to GL of V, as you might have expected, such that the map is continuous. What does that look like in this case? When we're working in p-adic land, that just means the stabilizer in G of each V is open. Okay, you can check that's equivalent to the usual notion of continuity in this case. And then admissibility, for any compact open subgroup K naught in G, the space of essentially K naught fixed vectors is finite dimensional. So the set of all V and V such that pi of KV is just equal to V for all K and K naught, that should be a finite dimensional space. So that's analogous to the definition of admissibility in the Archimedean case if you go back and look. How analogous is it? Well, we have Bernsteins Theorem, which says let pi be an irreducible unitary representation of G in some Hilbert space, H, and we'll let V sub K be its subspace of K finite vectors. That should probably be a V superscript K, but it doesn't really matter too much. Now here K is any compact open subgroup you like. The theorem says that then the restriction of pi of G to V equals V sub K is admissible in the above sense. So what is this theorem saying? This theorem is saying that the p-adic notion of admissibility is the analog of the Archimedean notion of a frac GK module. Now, in this case, though, something happens a little bit different. So in the p-adic setup, it's actually G that acts on V sub K, not the Lie algebra. We don't need to go to the Lie algebra to get the action that we want. So things are a little bit simpler in that sense. We can just use G itself rather than its Lie algebra. For more information on this theorem, you can see Bernstein representations of p-adic groups. Okay, how about unramified representations? An irreducible admissible representation pi of G is called unramified or of conductor 0 if the space of K equals GL2 of OF fixed vectors is non-empty. That's the correct analog of unramification in this setup. When we have such an unramified representation, it's a theorem that the space of K fixed vectors is actually one-dimensional, not just merely finite dimensional. And it's also true that pi is either one-dimensional itself, which means it's of the form chi composed determinant for some unramified character chi of F star, or it's just irreducible and it's actually one of these representations induced by characters, pi of mu1 and mu2 for some unramified characters, mu1 and mu2 of F star. So there's only two possibilities, and they're both sort of simple. But even if pi is ramified, there's still a notion of conductor. So I said unramified was the same thing as of conductor 0. So what is the conductor of such a representation? Okay, even if pi is ramified, there's still a smallest n and n called the conductor of pi, such that the space of all vectors V and big V, such that pi of the matrix A, B, C, D times V is the central character omega sub pi of A times V for all K and what we call K to the N is non-empty. And what is this K to the N? It's what we call a congruence subgroup of K, and it consists of all matrices of the form A, B, C, D, where C is 0 mod frac P to the N, where frac P is the maximal ideal of my ring of integers O sub F. Okay, and some other things are true. If N is the conductor of pi, then just like the case N equals 0, where we were dealing with just the K fixed vectors, it turns out that the K to the N fixed vectors is also a one-dimensional space. If you want more information on conductors and on a lot of the above information, you can see Castleman on some results of Atkin and Lehner or Jacques Shapiro. So that concludes kind of a brief overview of the p-adic representation theory of GL2. Starting next video, we'll look at some of the adelic representation theory of GL2. And so I'll see you then. Thanks for watching.